So the problems that we've looked at so far, we did a proof about that circuit satisfiability, that everything can, all problems can map to that. And now then we mapped circuit satisfiability to SAT. We mapped SAT to 3 CNF SAT. Okay. Now these are all about satisfiability and circuits. They all are very in the same family, so it's not too hard to do the mapping between them. But it's kind of interesting to see how we can take these satisfiability problems that are just about like Boolean circuits or Boolean formulas, and we can map them to problems that seem to be in completely different fields. So we'll look at how we can map this 3 CNF satisfiability to a graph theory problem called Clique. And we're not going to do the other ones, but the book also shows how other graph theory kinds of problems like vertex cover, Hamiltonian cycle, and traveling salesperson. Now these are all kind of graph theory problems, and it kind of makes it's not, once you're in the graph theory family, it's a little bit more natural to do those. But getting from the Boolean logic family to the graph family is kind of an interesting thing. And then we have this set partitioning one as well that we'll look at. So again, these are in seemingly very different kinds of fields or categories, but I can still map between this Boolean formula kind of problem into this partitioning a set into so that the sums are equal. So those are what we'll look at next. Okay, and so let's go to the graph theory one first. And we're going to look at the clique problem. So a clique in an undirected graph is a subset of the vertices so that every pair of the vertices in that set are connected by an edge in the graph. Okay. So the size of a clique is the number of the vertices that it contains. And so the clique problem in general is an optimization problem. Usually we think of like, let's find a clique that's the largest size in a graph. That would be an optimization problem that is important to find in many contexts. But of course we know we need a decision problem. So the corresponding decision problem clique asks, is there a clique of size k in the graph? Okay. So that's our decision problem, but you can imagine if you wanted to do the optimization problem, you could start with the largest number of vertices. Let's say you had, 12 vertices. You'd say, is there a clique of size 12? No. All right, how about size 11? No. How about size 10? Yep. All right, that must be the largest one, right? And so you could solve the clique problem by just decreasing the cliques, the number that you're looking for until you find an answer yes, and that would be the maximization problem. Okay, so an obvious way to solve the clique problem is to generate all the subsets of size k and check all the vertices and see if the vertices have edges between them. And if they did, then that would form a clique. Okay, now that k that you're asking about could be very near to the number of vertices over 2. Generally in graphs, if they aren't super sparse, we might have about half the number of edges divided by 2. And so if that were true and we generated all possible subsets, we would have v to the v, okay, which is not polynomial. So you have this feeling that clique is going to be a difficult problem and not solvable in polynomial time. So let's actually look at the proof that it is indeed NP complete. Okay. So first of all, if we were given a certificate, we want to show that we could check in polynomial time that every pair of vertices actually has an edge that belongs to the graph. And so could we do that in polynomial time? Well, sure, we would just go through every vertex in the graph and verify that the other vertices that were listed were in the adjacency list for each vertex. Okay, so we would have to go through each adjacency list at least once, but still that's polynomial in the It's in the number of edges. So we could check it in polynomial time. All right, next we need to pick a known NP-complete problem and polynomially reduce it to the problem Clique that we're thinking about. So we're going to do 3CNF to Clique. Okay. So we are going to start then with an instance of 3CNF. Okay, so that would be a formula in conjunctive normal form where each one of these clauses has 3 variables in it. Okay, so that's going to be an instance of 3CNF with k clauses, and then we're going to just, for sake of being able to talk about it, we need to take each of these clauses, okay, and say that the literals, there's 3 literals in this clause, 3 literals in this clause, right? Every single one has 3 literals. So we're going to name that with, okay, well, for clause R, the superscript is going to say what clause it belongs to, and that's literal 1 from that clause, literal 2 from that clause, and literal 3 from that clause. Okay. So now we're going to construct a graph so that this formula is satisfiable if and only if the graph that we construct has a clique of size k. So what does the reduction look like? Okay. So for each clause, we're going to place 3 vertices into the graph that we're building. Okay. So a vertex, and then, you know, we'll call this vertex 1. That's associated with clause R, vertex 2 associated with this clause, and vertex 3 that's associated with this clause. Okay. Very much like literals 1, 2, and 3. Okay. And then we're going to add an edge between 2 different vertices, okay, as long as those 2 vertices are in different triples, so they came from different clauses. Okay, so that's the first condition. And then also the corresponding literals in the original formula, they're consistent. That means we can't have like one of them be the negation of the other ones, because I couldn't and those together, or something can't be both true and false at the same time. So I'm only going to put an edge between them if they could both be true at the same time. Okay, so let's see an example of how this is going to work. So let's say I've got a formula in 3CNF. So notice this is a conjunction of disjunctions, and each disjunction has 3 distinct literals in it. So this is clause number 1. Okay, and so I'm going to make a vertex essentially for each one of the literals. Okay, so this would be, you know, this is going to be V1, 1, V2, 1, V3, 1. Okay, I look at the next clause. This is clause 2. That's over here. So this is V1, 2, V2, 2, and V3, 2. And my third clause here, these are the 3 vertices I add that are associated with that clause. So this would be V1, 3, V2, 3, and V3, 3. And then I'm going to put an edge between them. So first of all, notice I'm not going to put an edge between any of the vertices that came from the same clause. So I'm not going to have any edges among this group, no edges among this group, no edges among this group, because they came from the same clause. But okay, for each one of these, I'm going to go to all of the other edges and add, or sorry, all of the other vertices and add an edge as long as they're consistent. So over here, x1 and x1, those could both be true, and that they wouldn't interfere with each other, so I draw an edge. x1 and x2 could both be true at each side. That's not, there would be no problem with consistency, so I put an edge. x1 and x3 could both be true at the same time. Or one that could be true and the other one could be false. Okay, they won't interfere with each other, so I have an edge there. Okay, I move on to not x2. Okay, over here I'll put an edge. This comes from a different group, so I'll put an edge between not x2 and x1. Okay, they could both be true or false at the same time, and they're not going to interfere with each other. Okay, but when I come here to not x2 and x2, okay, there's no possible way for them both to be true at the same time. Right, that would be impossible, because if x2 is true, it forces this one to be false because they're concerning the same literal. So I can't have an edge between these two because they're inconsistent. I can't have them both true at the same time. But not x2 and x3, those could both be true at the same time. Okay. So I'm going to do that for every single vertex that I've added to my graph. Okay, so you'll notice, that there's not going to be, again, no edge between x2 and not x2 here. So there's no connection between those two. For x1 and not x1, there's no edge there. Let's see, for not x3 and x3, there's no edge there because those are inconsistent. Okay, so I put all the edges in other groups that I can, as long as it's not inconsistent. And so now I've changed from a Boolean formula in 3CNF form into a graph. Okay. And now we just have to convince ourselves that if this formula is satisfiable if and only if this graph has a clique of size k. Okay. So this one right here has 1, 2, 3 clauses. So I would be asking myself, is there a clique of size 3? So let's first of all look if this is satisfiable, that there will indeed be a clique of size 3. So if it is satisfiable, okay, I know that in each of these group of 3, I would have to have at least one literal that has a value of 1. How do I know that? Okay, well, if I have a bunch of things ORed together, for this to evaluate to true, I have to have at least one of these be true. Okay, so for this clause to be true, I have to have at least one of these literals to be true. Now, do I need this clause to be true for the whole expression to be evaluate to true? Yes, I do, because we've anded these things together. And the only way to, when I have a conjunction of things, the only way for that to be true is if each one of the things in my conjunction is true. So this has to evaluate to true, this has to evaluate to true, this has to evaluate to true. Okay. And so at least one of the literals in this, in clause 1 is true, at least one of the literals in clause 2 is true, at least one of the literals in clause 3 is true. Okay. And so any of the ones that are true, let's say I could put, color them 1s and 0s, and will I actually have edges between all of the between nodes in each of the 3 groups? Can I guarantee that? Well, yes, because as long as they weren't inconsistent, then I put an edge between them. So I will indeed have a clique that goes between 3 of the nodes that evaluate to true. Okay, so that's if this is satisfiable, then there has to be a clique of size 3 or of size k in general. And then we could also go the other direction. If I have a clique of size k, well, let's say I found a clique of size k, well, then for each literal that's associated with that clique, I could assign a value 1. Okay, and then I could just argue back, well, I would have at least 1 in the first clause, I would have a 1 in the second clause, a 1 in the third clause. If I had if I had a larger clique, I could put all of those clauses. I would know I would have to have at least 1 in each clause. And if there was at least one in each clause, then the formula would have to be satisfiable. Okay, so it goes both directions. If the formula is satisfiable, I'll have a clique, and if I have a clique, then the formula is satisfiable. Okay, and we could go through and do a proof that all of this happened. This is a polynomial time mapping. It can be done in polynomial time. Okay, we're just talking about 3 things and looking at edges for non-consistency. So hopefully you can see that it's pretty easy to do that in polynomial time.